then you're going to want to stand over by the X.
Thank you. Okay, can everybody hear me? Okay. Hi, everyone. My name is Rachel Morgan. I'm an optical scientist with the SETI Institute and NASA Ames Research Center, and today I'm excited to tell you about some recent laboratory testing results with the AstroPIC integrated photonic coronagraph. So first, I'd like to acknowledge the rest of the team. A lot of us are here today. The AstroPIC project is led at NASA Ames Research Center by Dan Serbu, the PI, and Russ and Eduardo are also here, also John Lin from our group. We collaborate a lot with the Integrated Photonics group at Stanford. They are experts in programmable photonics, which has been really helpful. And we also have external collaborators from other institutes. So I'm going to start with a motivation for why we want to use integrated photonics for coronagraphy, and then I'll talk about the development of an integrated photonics testbed at NASA Ames, and highlight some recent results that have seen very good extinction ratios in the testbed, and then I'll finish with some next steps. So as we've been hearing all week, there's a lot of scientific interest in studying Earth-like planets around other stars. But this is an immense technical challenge. A lot of very, very smart people in this room and elsewhere have been working on this for many, many years. It requires extreme levels of wavefront control that are extremely hard to achieve. And the instruments are very sensitive to mechanical and thermal effects that are kind of inevitable in a space environment. And they're extremely complicated to design and implement, which means that the instruments end up being very large and very expensive. This is a plot of the expected exo-Earth yield, so the total number of Earth-like planets characterized by a habitable worlds-like mission as a function of the effective telescope diameter. And you can see that there's kind of a gap. These are the existing technologies down here, and compared to a theoretical upper limit, there's kind of a gap in efficiency. That's not caused by fundamental physics, but more limited by technology. And that theoretical limit has actually been calculated by Guyan and Belikov, where they describe a coronagraph as kind of a transformation between an input telescope plane and an output science plane. And in between, they put just like a random matrix that is mapping between those two places. And they tried to figure out what the best matrix is to most efficiently separate out the starlight while preserving the planet light. And so there should exist some matrix that does this properly. And conveniently, other researchers such as Reck, Miller, Clements have all proposed that if you have enough tunable interferometers, you can actually devise a system that can implement any matrix. So any optical system can kind of be described as a multiplication of many different transfer matrices representing the different components. And so that system matrix can then be decomposed to look like the multiplication of transfer matrices corresponding to different interferometers. And so we basically do that transformation, and then we miniaturize all those interferometers onto a photonic mesh. So we use integrated photonics to have a practical way to actually fabricate this sort of universal photonic processor. And the benefits of this is that we could have extremely small devices. I actually have a display chip here, which is too small to be seen from out there, but here, you can pass it around if you want. But yeah, we have extremely small devices that are also very robust. Because they're so small, it's kind of nothing you can really do to them affects them so much. And we also hope that it can improve the efficiency of coronagraphs, particularly at very small inner working angles, and improve the risk margins for missions such as HWO. So here's an overview of the design of AstroPIC. So we're going to be coupling light from the pupil plane of the telescope, and then we use a microlens array to concentrate the light onto a set of grating couplers. These grating couplers then diffract the light into these waveguides, and then the waveguides lead the light into this integrated photonic mesh of interferometers. Our PIC device has 9 inputs and 9 outputs right now. This is a picture of the first AstroPIC prototype with all the wire bonds, and then this is a dime for comparison. So the device is very small and very scalable. Here's kind of an overview of the concept of operations. So we have the input light is kind of a mix of the starlight, which we don't want, and the planet light, which we're trying to separate out. And then this mesh is implementing a spatial mode sorting algorithm. And so up here, you can see that like this one diagonal has sorted out this bright spatial mode. And then as we go down the diagonal, it's more spatial modes getting sorted out. And so we're trying to concentrate as much of the light into these upper spatial modes, leaving these other modes to be dark channels that we can then use to study the planet light that gets through. And then from here, the light from these channels can then be sent to another instrument, such as a spectrograph, for further characterization. So here is a layout of the first generation AstroPIC chip. So this is the chip that's getting passed around right now. It actually has two different chronographs on it, but I'm going to talk about just one of them today. It has 9 input grading couplers that are arranged in a 3x3 grid. It has 72 integrated phase shifters, so there's 36 Mach-Zehnder interferometers across the mesh. And then at the output, we have all of the grading couplers are kind of in a line here. And so we can put a fiber array at the output to monitor all of the output channels. So in order to test this device, we had to build a photonic testbed at NASA Ames. Some of the key components of this is we have a laser. We have a tunable laser, but we're testing everything monochromatically right now. And then we send the light. We have to control the polarization. Most integrated photonics devices are designed to operate in TE polarization, but there are other designs that can operate in TM. And then we send the light onto the PIC, which is hosted on a control PCB. So we use an NI DAC to send voltage commands to all of our different phase shifters in order to control the phases of these integrated interferometers. The output of the chip has a fiber array, which then sends the light to a bunch of different photodetectors, which are read out using the same DAC and read out to the computer. And the goals of this testbed are to demonstrate that the AstroPIC prototype chip can operate as a chronograph and also identify key issues to inform future iterations of the design. So here's a picture of the testbed set up at NASA Ames. So in this picture, you actually can't even see the PIC, but it's down here. And then this is like the spaghetti of optical fibers coming out of the fiber array and connecting them to all these different photodetectors over here. And here's a zoomed in shot. So this is showing a cleaved optical fiber, which is one way of sending light into the chip, lined up to an input grading coupler here. These are the wire bonds that send the voltage commands to each of the different phase shifters. And then this is a fiber array at the output, which picks the light off of the chip and sends it to the photodetectors. So now I'm going to highlight the basic building block of this device, which is a Mach-Zehnder interferometer. So this is a 2-arm interferometer with 50-50 directional couplers, and then 2 different degrees of freedom. So we can use the phi phase shifter to control the relative phase coming into the device, and then the theta phase shifter to control the splitting ratio of this interferometer. And so this is showing the effect of sweeping that theta phase shifter. And so you can see that the light is switching between the 2 outputs. And then this is a plot of showing a voltage sweep. So again, with that same theta phase shifter, if you sweep the voltage very carefully, you can actually get a very, very deep contrast. You can get a very deep extinction ratio at a single voltage state. So we've actually measured upwards of 10 to the minus 8 extinction ratio just with a single interferometer being used, which is pretty crazy. So the first type of experiment I'm going to describe is the single channel minimization. So for this experiment, I line up the input cleaved fiber to the upper grading coupler here, and then I'm using the mesh to try to minimize as much as possible the signal that reaches over here. And then I think to do it this way. This is a video of the procedure that's used to do that. So essentially, we just sweep across the full voltage range and then keep sweeping across that minimum state and just reducing the voltage range that we're sweeping across until we reach the resolution limit of the DAC we're using to control the phase shifters. So here is a plot of one of these single channel minimization experiments. We actually start from a pre-calibrated state that is designed to be a pass-through state. So as close as possible, we're trying to make it seem like the mesh isn't there to start. And so that actually already does a very good job of isolating the single channel input from the output, just because they're physically separated. And so that gives us about 3 times 10 to the minus 9 starting extinction. And then from there, we can control the mesh, the different degrees of freedom, in order to correct this pre-calibrated state and also control the path of back-reflected light that is bouncing around the chip. And so by doing that very carefully and very patiently, eventually you can actually get the contrast to go down. And in this case, we were able to get a final extinction ratio of about 3.5 times 10 to the minus 10. And then from this nulled state, I actually swept that tunable laser source in order to get a sense for the chromaticity. And so those results are shown over here. And as you can see, it is a pretty chromatic effect because this is based on interferometry and the way we're applying a phase shift is dependent on the wavelength. This minimized state is really only true at one specific wavelength, but in the future we hope that redesigning the 50-50 splitters and the phase shifters to be less chromatic will help the overall system be less chromatic. So next, we did a more realistic type of demonstration where we actually had a circular pupil as the input instead of a single fiber coming in. So in order to do that, we built this free space coupler module. So this has a laser source over here, and it re-images this pupil that we can put into this slot here, and it reduces it by 10 times and re-images it directly on top of the chip. So this is a picture over here of the output of that free space module. So we have a nice circular image right there, and then the grading couplers are kind of overlaid for scale. In order to increase the sampling efficiency, we align then a microlens array over top of the grading couplers, and this helps concentrate the light onto the grading couplers to improve our throughput. So here is that microlens array, which is really, really close to the top of the chip. That's aligned with the 6-axis stage. So for this type of testing, we're actually implementing a mode sorting algorithm. It's a self-calibrating algorithm that's been developed by our collaborator at Stanford, David Miller. So he has a paper from 2013 that kind of summarizes the approach. But essentially what this algorithm is trying to do is decompose the light into its constituent modes. It's kind of like doing an SVD. It's kind of picking out the brightest eigenmodes of the system. So to start, you go diagonal by diagonal in this architecture. So I use the Mach senders and tune all the phase shifters along this top diagonal in order to maximize the amount of light that gets into channel 8. So this was the light in each of the output channels kind of imaged from above before applying any voltage. And then this is after sorting out the top mode. From there, we went down to the second mode. And so we have 2 bright outputs, and the rest of them are a lot dimmer now. And then I kept doing this along the diagonals. And so this is what it looked like when all the modes had been sorted out. And at this point, we have about 5 × 10⁻⁵ extinction in this bottom channel 0. At a certain point, though, there's not enough light remaining in these output channels to really reliably do that maximization algorithm. You're kind of just sloshing light around. So I started to just directly minimize the amount of light in channel 0 instead of maximizing the light in the top output channels. So using that approach, I was actually able to get the signal in channel 0 down to about 8.8 × 10⁻⁸ extinction ratio. And so that is shown here. So the blue line is the light before this is in a path-through state, but before sorting the modes. So you can see that the light is relatively evenly distributed. And then this sorted one has the bright channels up here, and then the remaining light is pretty minimized in this output channel there. And then to test this in a more realistic sense, we also need to know where the planet light would go, like an off-axis source. So we actually move the input source slightly, which changes the angle that the input light is hitting on the input grading couplers. I don't know exactly by how much because it's currently like a mechanical knob that I was twisting, but in the future that will be replaced with something that's more controllable. But this green line shows that when you move the source to a little bit off axis, we actually get about 20% throughput into that channel 0 without touching the mesh. So it's the same state on the mesh. So currently, this is kind of a summary of the limiting factors that I think are limiting us right now. So one of the big ones is throughput on the PIC. It's only about 1 to 10%, depending on which strategy we use to couple light in and out. And this is mostly limited by the grading couplers that we're using to couple light on and off. They only have about a 35% efficiency at best. And so there's actually our collaborator at Stanford, Carson Valdez, who recently graduated, has developed a higher efficiency grading coupler design based on an adjoint optimization technique. And those have been measured in the lab to have over 85% efficiency. So incorporating those will actually increase the throughput to about 50%. If we then also consider other material platforms, we're currently using silicon on insulator, which is about 1 decibel per centimeter of propagation length. It's like this kind of standard loss in that platform. We could also consider silicon nitride waveguides, ULI, other different platforms that have lower propagation losses. And so we can estimate that with a combination of different materials or different coupling approaches, we could get the throughput up to about 70 to 90% maybe in the future. The bandwidth is another key challenge. So currently it's quite limited, as we saw before. But by changing each of those subcomponents to be less chromatic, we could put them together to develop a system that is overall less chromatic. Some other challenges are the Fabry-Perot cavities on the chip, but having more efficient coupling will just reduce the amount of light that's not getting out, and that will naturally kind of reduce the amount of light that's bouncing around on the chip. We also see a lot of thermal crosstalk, which is very annoying. But there are fabrication strategies that can mitigate that for thermal phase shifters, and also there are non-thermal phase shifting options too. Yeah, and then the field of view currently is kind of limited by the number of channels we have on the PIC, but in a future iteration, we plan to increase this channel count. So here's kind of a brief summary of the next steps. So this is data from that very high efficiency grading coupler I was mentioning before. There's also a vacuum testbed coming online at Ames in the near future, and we plan to test AstroPIC with this vacuum testbed in the near infrared. And then there's also this algorithm that's been developed by Kevin Fogarty that shows that while the mesh, even with some chromatic effects in the components, you can use the extra degrees of freedom to actually expand the bandwidth of your high contrast. So yeah, in conclusion, we've had some good results so far. Yeah, thank you very much.